Hey guys, what's going on? My name is Sean, and today we are doing picoCTF and starting with the first binary exploitation challenge, Stonks. If you're new to capture the flags, this is a great one to get started with, and I by no means am an expert, so we'll get through this one together, and I hope you learn something and enjoy. So reading the description, it says, I decided to try something no one else has before. I made a bot to automatically trade stonks for me using AI and machine learning. I wouldn't believe you if you told me it's unsecure. And I always check out the hints, and the hint says, okay, maybe I'd believe you if you find my API key. It also gives us a link to the vulnerable source code and a way to interact with the program online. So I've already gone ahead and downloaded the source code, which you can use wget, or you could just click and download it. Yeah, let's try interacting with this over the network. So I've just copied the netcat command here, and yeah, let's see what happens. So it says, welcome back to the trading app. What would you like to do? Buy some stonks or view my portfolio? We'll go with the first option, buy some stonks. And it asks us for an API token. I, of course, don't have one, so we'll just try out something random. And it looks like it spits out some stonks for us. Now let's go back and take a look at portfolio, and it says we don't own any stonks. Okay. Maybe something happens if we, say 3 or something like that. Okay, so it just prints out goodbye. So before we move on and look at the source code, which might provide some more information about the program, let's take a look and just recognize the two places that we have user input going into the program, which is key to having like reproducible and recreatable bugs. So the first one is right here where we provide the one or the two. We control that. And we also control what our API token is. So just take a note of those two things. And when we're looking through the source code, that might also provide us with some key insights. So I'm just going to open the source code with VS Code here. I think it'll make it a little bit easier to look at. And the very first thing that I like to look at is main, regardless of anything else in the program. I think it just gives me a good understanding of what's going on in the control flow. So yeah, let's take a look. The first two lines are not super important. It's just saying when to print out characters and basically creating a seed. We're initializing some structure called portfolio, and then printing out some information and receiving our first user input here with this scanf. So what this will do is take the user input and cast it as an integer and store it in the address of resp. So if it's a 1, then we'll buy some stonks. Otherwise, well, not otherwise. If it's 2, then we'll view the portfolio. Otherwise, we're going to exit the app. So that's what we saw when we provided 3. So let's take a look at this first function, buy stonks. It already had it there for me. So if we look at buy stonks, it takes as an argument a portfolio, and we're going to initialize a static buffer of flag buffer size. And how large is that? Our preprocessor macro says 128 bytes. And then we're going to open this API file, which we don't have on our system. And it says flag file not found, contact an admin if the flag doesn't exist. Okay, so this is a pretty good insight into, telling us that the flag exists inside this API file. It then reads from this file 128 bytes into our stack base buffer. This is where it's buying our stonks. So we are initializing some things and then getting a random amount of money and then buying our I'm sure, really good stonks. I'm sure it's not random at all. But we could take a look at this function later after we get through this one, perhaps. And then it says, that our stonks are chosen. Here we see some to-dos. So to-dos in source code, always a good indication that you should be examining that part of the source for bugs. It usually means the developer didn't quite get around to what they were working on, and maybe not everything is implemented exactly how they want it. So we're going to create a heap-based buffer of 301 bytes, ask what the API token is, and then take in 300 characters and place that into the user buff. And we're going to print out the API token that we gave the program. So this is why we see test being repeated to us after we've already provided a test. And actually, this is where the bug is, right? So this is what's known as a string format vulnerability bug. And well, we'll get into why. So this is a typical use case of printf, right? The meaning of life is, and that %d will be replaced with a 42. This is what we're all kind of used to. That %d being our string format character. So there are a number of them, right? We have decimal, unsigned decimal, hexadecimal, string, and then %n will write into the argument the number of bytes that have been output or written so far. And this is by no means exhaustive. But what happens if there's a mismatch between the format string and the actual number of arguments provided? So say, for example, we have, again, the meaning of life, and then say our favorite number is %d, but we've only provided it with 42 here. So there's only one argument. Like, what is that second %d going to be? And surely the compiler would check this, right? Like, we know how many arguments there should be. Well, if we look at the man page for printf, we'll actually see that that's not the case because it takes in a variable number of arguments. So the compiler is not going to catch this. So at runtime, whenever printf executes, it's going to expect those arguments to be either in the registers or the stack, depending on what calling convention, what architecture you're on. But it's going to expect those things to be there. And if they're not there, well, it's still going to look in the registers of the stack anyways, and it's going to pull from those locations and, carry on with its execution. So how can we use this maliciously? Well, there's a number of things that we can do. The first one is we could crash the program. So in this case, the %s, this will, pop off of the stack the arguments that it needs, and or examine the registers or both, and treat them as pointers to strings. Well, not everything that's going to be in those registers of the stack are going to be pointers to strings, and on that dereference, we're going to get an invalid memory read, and it'll crash the program. The other thing that we could do is view the stack. So in this way, we can walk up the stack, and this is just printing it out a little bit nicely, and see what's there. We can get an arbitrary read similar to the %s thing that we were doing before, as long as we know that we have a valid memory location to read from. Or we can have an arbitrary write. So our %n in this case will write to the address of I, the number of bytes that have been output so far. So in this case, we have 1, 2, so I would be 2 because we've written 1. All right, so knowing these things, how can we use this to our advantage? Let's go back to the program and let's just provide it with a bunch of %s's, and we'll see what happens then. So I'm going to netcat back into it. I'm going to say I want to buy some stonks, and for our API token, I'm just going to put in a bunch of %s's. All right, so we got a core dump, we got a core dump. This means that we have successfully crashed the program. It has dereferenced a pointer, and that wasn't a valid memory location, and it crashed. Okay, what if we were to walk up the stack? Let's try that. So in this case, we'll just do, okay, so in this case, we actually got some valid data back. This is all data that's on the stack, represented as hexadecimal, and this is valid. And what else did we see in our source code that was on the stack? Well, our API buffer, right, which eventually has our flag written to it. So maybe part of this is our flag, and maybe we haven't walked up the stack far enough. Let's try doing this again, but with more %x's. And we'll just do it in Python. I think I'll be able to do it a little bit easier. We'll say 30. I feel like 30 should be good. We'll do that. Okay, so we've given it 30% x's, and just going off of a few of these numbers here, they do look like ASCII, and it's hard to tell if you haven't messed with this before, or if you haven't messed with hexadecimal before. But there's a really great tool, also in the man pages, man ASCII, will show you the hexadecimal representations of these characters. So like 41 being the uppercase A, all the way through like 7D is probably what we're going to be concerned with. And so 6C falls right in there, and so does 30. That's probably a lowercase number. Yeah, so I think our flag is in here. And I'm not going to do anything fancy. I'm just going to take this and I'm going to put it in a hexadecimal to ASCII converter. And well, let's just see what we get. So let's just go to Google real fast and do a hex to ASCII. And we'll go to the first one. I'm sure it'll be fine. And I'm just going to paste that there. We'll convert it. And what do you know? This looks like it should be our flag. But why is it kind of, it's not backwards. Only the like 4 characters in a row are backwards, and then it kind of flips. But this is our flag. We just need to reorder it. And I will leave that as a challenge for you. And I won't bore you with how to do that on stream, but take a look at the Pwn Tools P32 function. And if you get stuck, I will have a link to my GitLab below, and you can take a look and see how I did it. So thank you so much. I hope that you learned something today. Hope that you had a great time, and I will see you again next time for the next challenge of picoCTF. Thank you.